Urgent, the sky turns red, and the ground beneath you shakes as a massive, impossibly close moon dominates the horizon. This is a hypothetical apocalypse. In reality, our oldest companion orbits at a distance of 384,000 kilometers, a gap wide enough to fit 30 Earths. This visualization illustrates the physics of a stable orbit. It is a state of permanent fall, where gravity pulling the moon inward is perfectly countered by its lateral velocity pushing it outward. Traveling at 3,680 kilometers per hour, the moon moves sideways fast enough that the Earth's surface curves away beneath it at the same rate it falls. Our safety on the surface is bound to this orbital geometry. As long as the moon maintains its lateral speed, it stays exactly where the physics require it to be. If an external force, like a rogue planet passing through the solar system, were to slow that lateral speed, the orbital equilibrium breaks. This visualization tracks the result, a decaying spiral orbit. Because gravity obeys the inverse square law, its pull grows exponentially stronger as the distance shrinks, accelerating the moon toward us over the course of a year. This collision isn't a single event, but a series of catastrophic thresholds that dismantle the planet piece by piece. Within the first few months of the decay, we cross the first threshold, hydrological collapse. As the moon draws closer, its gravitational pull on the oceans increases. Global tides that normally rise a few meters transform into 20-meter surges. These walls of water permanently submerge coastal cities twice a day, effectively erasing the world's major ports. By the midpoint of the year, we reach the lithosphere limit. The gravitational pull is now strong enough to grip the solid rock of the Earth's crust. This gravitational flexing generates massive stress on tectonic plates, triggering megaquakes in regions that have been seismically silent for millions of years. This photograph of the volcanic eruption captures the scale of disruption. The same gravitational stress squeezing the Earth's mantle forces magma to the surface, filling the atmosphere with ash and electrical discharge. Long before a physical collision occurs, the moon's gravity has already rendered the Earth's surface uninhabitable. This chart shows the Roche limit at 18,000 kilometers, where Earth's pull overpowers the gravity holding the moon together. Because Earth pulls harder on the near side, the lunar body stretches until it shatters into debris. Saturn's rings serve as historical evidence of this process. Astronomers believe they formed when an ancient moon drifted inside Saturn's Roche limit and was torn to pieces. As the moon dies, its fragments form a debris ring around Earth. These falling pieces create a continuous meteor storm, setting the atmosphere on fire. Finally, what remains of the moon's core, a mass of dense rock 3,400 kilometers wide, strikes the Earth. The asteroid that killed the dinosaurs was 12 kilometers wide. The moon's core is nearly 300 times larger, releasing billions of times more kinetic energy. This impact doesn't just end life. It melts the Earth's crust into a global ocean of magma and strips away the atmosphere entirely. Earth is left as a silent, glowing ball of molten rock floating in a vacuum. There is a historical irony here. This scorched, post-impact world looks identical to the Earth 4.5 billion years ago, moments after the moon first formed. The physics that end the world result in the same landscape that witnessed its beginning. In reality, we are in no danger. Measurements from NASA's control centers prove that the moon's trajectory is stable and actually moving 3.8 centimeters farther away every year. At its current distance, the moon's gravity is actually a stabilizing force. It locks the Earth's axial tilt in place, giving us the predictable seasons that allowed life to evolve. The moon's gravity acts as a constant regulator for our world. It provides the tension necessary to stabilize our axis, keeping our environment predictable and our existence possible.